So here, to give you an idea of what we're going to learn today, we're going to do a quick review of R. We're going to talk about what scaling is. We're going to talk about data theory. We're going to talk about first summated rating scales. We're going to talk about principal components analysis, factor analysis, and multidimensional scale. So this is going to be a really quick review of R. So hopefully you all have some idea of R, but if you don't, you can actually learn this by this and by what we're going to see. So in R, fundamental concepts are objects. So objects are basically computer creations that store information. And the way they store information is by assigning information to them. So essentially in R, what we do is we use commands and we perform them on input objects, and then we assign their output using this operator here to output objects. It's really simple. In R, that's what we're doing all the time. And you'll just see that when we do it over and over again, and that's what it's all about. And the commands are stored in packages. So unlike other programs, often the commands won't be loaded by default. You actually have to load the packages before you run the commands. So just to give you a general idea of how this all works, so here you perform a command on an input object and you assign that output to the output object. That's basically what we're doing all the time in R. Okay, so that's our quick review of R. Any questions? Okay, so what is scaling about? So scaling is all about optimizing the information we have. So we have information that comes from our observations, from our study or survey or whatever we're doing, and we want to find the best way of representing that information. And we represent that information in data, which we can then use for empirical analysis. And we're essentially looking for two things. We're looking for power. We want to be able to explain as much variance in information as possible, but with as few dimensions as possible. So with parsimony. So we want as much power and as much parsimony as possible. So as much variance with as few dimensions. Dimensionality refers to how many important sources of variability there is among the objects. So there are a number of different sources of variability, and we'll see some examples of this. And we generally want to reduce the dimensions, so have as few dimensions as possible, as few important sources of variability as possible. And generally, in scaling, we can present the results graphically, and that's one of the major advantages is because there's a major problem with data in general, which is called the curse of dimensionality, that there tend to be so many dimensions that it's just impossible to present our information graphically. But if we use scaling techniques, we can often reduce our data to 2 or 3 dimensions, which can be presented in a quite effective way graphically. So, has anyone heard of data theory? So data theory is something that's really cool. It really gives you a lot of freedom, and it really helps you understand what it is you're doing when you're doing an empirical study. So data theory is the study of extracting information from empirical observations. So essentially we have observations, and we're looking at how we turn those observations into data. That is data theory. So we use various techniques and we produce data which we can then use for empirical analysis, for regressions or whatever we want to do. And actually we always have an implicit, if not explicit data theory. We always have a data theory. Even if we're just using survey data, we download a data set and we say, I'm not using a data theory, I'm just using the data. No, you actually have a data theory. There's actually an interpretation of what the observations are. You have observations. For example, if you're using a survey and you have a question, ask people for their vote intentions. Those are observations. You have people who said they wanted to vote for party A, party B, party C. And you have people who said they refused to answer, people who said they don't know. Those are all observations. What you do with that becomes your data. You can decide to ignore everyone who didn't give a party. You can decide to ignore everyone who didn't say they would vote for one of the 2 biggest parties. You can actually not ignore all that, and also often you'll have information on how long it took people to answer. So you can create data from that. So all of these are observations, then you will decide what you do with it, and you will turn those observations into data. That's what data theory is all about. So it's either explicit or most often implicit. Often we'll just use what seems like the most obvious information that we have in our data sets and create data out of that. As I said, knowing about data theory gives us a lot of freedom because we can actually be really creative and find the best way of representing information and then the best way for empirical analysis. So it is actually a really good thing to know. We understand that information is so much more complex and it's not just simple data as we tend to see it. Does everyone understand that? Any questions? Okay, So quick introduction to data theory. Here there's one example. There's this guy Clyde Coombs, who in the 60s came up with a data theory, and he said that there's essentially 4 different types of data. Today we're going to talk about 2 types, and we're going to talk about there's scaling methods you use for them. So I think these are the 2 most common types in social sciences. The other 2 types aren't quite as common, and the methods are more complex, so we're not going to talk about them today. So the first type of data is single stimulus data. So in single stimulus data, we're essentially trying to place objects along 1 or more dimensions. So there are many different examples here. So it could be that we're trying to evaluate people's intelligence. So we want to place people along a scale of intelligence. So it's a single stimulus. So there's 1 scale, and we want to place people along that. Actually, it could be 2 scales. The basic idea here is that you have individuals, it could be any kind of object, it could be countries, cities, whatever, and you want to place them along some dimension. You'll understand in contrast with the other one. So it could be people in intelligence tests, it could be server respondents, you want to place on a left-right scale, it could be many different things. And the types of scaling techniques we use here are summated rating scale, principal components analysis, and factor analysis. We're going to see all of those. So it's the basic idea of placing objects along 1 or more dimensions. So that you basically have 2 sets of things, objects and dimensions, and they're 2 different things. Well, the next one we have 1 set, but we have different objects in the same set. So these are similarities data. Here we're looking at how similar 2 or more objects are. Actually, we're often looking at how dissimilar they are, how different they are. And here, this is basically the proximate relation between pairs of objects from the same set. So it could be how similar 2 cities are, how similar 2 political parties are, 2 political leaders are. And here, the kinds of methods we use are called multi-dimensional scaling, and that's the last scaling technique we use. So the first type, single stimulus, is when we have objects that we want to place along dimensions. So they're different sets of objects, different types of objects, whereas the second one is the same type of objects that we're comparing amongst themselves, and we want to show how similar, how different they are. Okay, now let's talk about our first scaling technique. Are there any questions at this point, or is everyone okay? Okay, so our first scaling technique. So for single stimulus data, this is the most simple technique, and I'm sure you've all encountered this technique in the past. A lot of people don't apply it right, and you'll understand how we can ensure that we respect the assumptions under the technique. And I think it's really important because often scales are actually not as reliable as we think because we don't necessarily use the right tests. So the idea behind summated rating scales is that we have scores on n different units, so individuals, cities, countries, but we have those scores on k different items. So we know for n people, their score on k questions, so the way they answer k different questions. And we consider those items imperfect observations on an underlying characteristic. So we assume here that there is some underlying characteristic we're trying to measure. And we have k different measures of it, but all of those are imperfect. None of them perfectly represents that underlying dimension. So they all contain error. So we want to put them together to try to find the most pure measure to eliminate that error. The major assumption here is that they're all scored in the same way. If they're scored differently, the one with the most variance is going to take over the scale, which we want to avoid. So often we'll standardize our scales. But actually, we generally take items that have from 0 to 10, 0 to 1 to 4, whatever. We want them all to be scored in the same way. So essentially, what we're doing when we create a summated rating scale is that we collapse across the columns. That means that we take the mean within each row. So for each individual, we take their mean on a number of questions. Sometimes people will actually take the mean, they'll take the sum, but then you end up with a larger score. Generally, it makes more sense just to take the mean. It's the most common thing. But once again, a huge assumption here is that there actually is an underlying dimension. This is the one technique where we really don't test for dimensionality at all. We just assume that all our items have some underlying dimension. Because there's a major risk here. If there isn't, you can actually create false positives. You can create false scales that represent a dimension that doesn't actually exist. So it's something we're going to see how to avoid that. It's a major major obstacle in having a way. We always want to make sure that our scales actually represent something that exists in the real world. Any questions? And by the way, so Likert scales are the most common example of summated rating scales. It's actually pronounced Likert, not Likert, as many people say. There are actually 3 different models of summated rating scales, but that's the most common one, which is basically what we're doing today. So why do we want to create a summated rating scale? Well, one reason is that you want finer resolution. So if you have one item that is, that a dummy variable coded 0, 1, it basically divides the dimension to 2. So you don't have that detailed measurement. Now if you add 2 of those, 2 dummy variables together, it divides the dimension to 3. Each time you add an extra item, it divides the dimension more and more. So if you have k items with m categories, you end up with this many distinct scores. So it's k times m minus 1 plus 1 distinct scores. So you really increase the level of detail you can measure your underlying dimension when you add more items. And essentially, theoretically, if you add more and more items, you can actually increase the level of measurement. So if you have items that you consider ordinal items, they're measured at the ordinal level, if you add up a large number of them, you can consider your scale to be an interval measurement. It's really cool. You can actually move up a level of measurement by creating a summated rating scale. But probably the major reason why you want to create a summated rating scale is to reduce measurement error. As I said, we assume that all of our individual items contain error. So each item consists of the true score plus some error. So Bij is the item for individual I, and it's item j, plus Ti, the true score for individual I, plus error I for item j. And we assume that the expected value of the error is 0. So when we add up all these items, the error should cancel out, and we get closer to the underlying dimension as the more items we actually have. So reducing measurement errors is a key reason for creating items. It's trying to create a measure that is more that reflects the actual underlying dimension. One huge assumption that you really have to keep in mind when creating a summated rating scale, other than the fact that the dimension actually exists, probably the other one, which is actually huge, and I think it's the one that's most often ignored, is that you expect there to be a monotonic relationship between each item and the underlying dimension. And that's something that people rarely ever test for. People often look at correlations, Cronbach's alpha, but they don't measure that. They don't tell you that. We're going to look at some graphs and we're going to see how you assess that. So it's really important. So the assumption is called monotone homogeneity. So there should be a monotonic relationship between each item and the underlying dimension. So monotonic means either it's always increasing or always decreasing. It can not increase at one point, so there's this distinction between strict and weak monotonicity. So it doesn't necessarily have to increase all the time, but it can't. If it increases, it can't decrease. It's really important. And we'll see what that looks like in some graphs. So how do we verify our assumptions, especially the assumption of monotone homogeneity? So basically what we do is we do an item analysis. So we'll look at each item individually, and we'll make sure that it has a monotonic relationship with the underlying dimension. Generally, it's best not to use correlations. So there are many different ways you can use correlations to assess a scale. One way is assessing the correlation between each item and the whole scale. If you do that, the problem is that the item is included in the scale, so it affects the correlation. It doesn't really make any sense. The other ways you can split the items in half. There are many different ways, but the major problem with using correlations is that correlations measure linear relationships. Correlations are not made for assessing monotonic relationships, which is what we're looking for. So it actually deflates the relationship between the items and the scale because it's looking for linear relationships. So correlations are not great to use. Cronbach's alpha is also not a great thing to use because it is also based on correlations. Cronbach's alpha assesses the correlations among a set of variables. So again, it's correlations, it measures linear relationships, which is not what we're looking for. We will use it, but we want to use it alongside graphs which assess the relationship between the items and the underlying dimension. So as I was saying, so we look at graphs showing the item versus the scale without that item, because we don't have the true dimension. What we do have is we know the scale, and we do for each item, we assess the relationship between that item and the scale taking out that item, so we can see whether there actually is a monotonic relationship. And that scale is called a rest plot. And so essentially it's a scatter plot, and we include lowest non-parametric regression line to look at their relationship. Any questions? There were a few potential problems with summated rating scales. So we rely on the assumption that there actually is an underlying dimension. So if it doesn't exist, we have a problem. And there often are cases of false positives. Often, if you're looking at Cronbach's alpha, it might actually be extremely inflated, and one of the major causes of that is when there's clustering in the items. So let's say you have 6 items, if 3 of them are highly correlated, and the other 3 are highly correlated amongst themselves, but there's no correlation between those 2 clusters, you can have an extremely high Cronbach's alpha, but there actually be no underlying dimension, or really 2. So you can have false positives if you just look at Cronbach's alpha. You really have to be careful that a dimension actually exists, so it's a huge problem. If you ever have any doubts about the items, that they actually reflect one underlying dimension, it's probably best not to use a summated rating scale. The other methods are probably better, because they do allow for multidimensionality, and they can actually verify what the dimensionality is of behind our variables. Okay, so now we're gonna get into R. So hopefully everyone has R Studio. It makes it a lot easier to look at these things.
Okay.
So in R Studio, has everyone used R Studio before? So you know that you have a code up here in the upper left-hand corner, and then you have the console here where it actually runs the code. So we're going to start by running some of this stuff. So some basic R, you all know that a number sign means that they're comments. So I've added comments in here, so you can go home after and look through the code, and everything is pretty much explained, so you can go over things on your own. And again, as I said, most of the commands, or a lot of the commands, well, basically all the commands at some point are in a package. So you have to load those packages. So the ones that aren't loaded by default, you'll have to load, and you load them using the library command. So first we're going to load 3 packages. Foreign is used for opening data sets, which are in foreign formats, so Stata, SPSS. So we're going to need that because our data sets are in Stata format. So basically what we do is in RStudio, you can either select the commands, or you can just click on the line, and it will run the command in that line. So here I'm just going to click on the line with the library foreign command and run it. So it ran that, and now we have the commands that are in the foreign package. Next, we're going to load the lattice package, which we use for graphs. Now we're going to load the Mispsycho package, which has a number of tools for making summated rating scales. So we're going to, now we have all those. And now let's load in our data set. So one thing that makes it a lot easier to load data sets is to put the data sets in the same folders where as you have your code. So the same folder as the code. And that makes it really easy because then all you have to do is set the working directory to the directory where you have the code. And you do that by clicking on Session, set working directory, and the source file location. And now you don't have to tell R where the files are, it knows already where they are. So now we'll load a data set by clicking on this line here. So here we're using the command read.dta, which opens data files. And we apply that to this file name, ces11.dta. So we load the data and then we assign it to object ces11. So ces11 is a subset of the 2011 Canadian election study. I've taken 6 different variables that measure confidence in various different institutions. And the idea is we're going to try to create a scale that measures confidence in institutions by putting those together. I've eliminated all missing values, so you might wonder why the number of observations is smaller than it would be. And in CS, that's why. And I've also converted all the variables to numeric.
Why did you? Because do you really have to eliminate all missing values, or I mean, the technique allows you to build a scale although there is some missings?
Well, they won't fit in the scale if they're missing values. You have to do that to create a semi-numeric scale. So we have evaluation of courts, civil service, police, federal government, provincial government, elections, Canada, so confidence in all those institutions. So if we want to look at the data, at the variables we have, we can run the command summary on the data set, and we see that it gives us a summary of the data, so it gives us the minimum, maximum, mean, median, etc. So we can see that they're all scored the same way from 1 to 4, which is what we need to create a rating scale. Let's standardize them. It isn't really necessary, but it's sort of conventional. And so we standardize the values by using the scale command. So the scale command we apply to the data set, which is CS11, and then the scale command produces output in the format of a matrix. But we actually want a data frame. R stores data sets in the form of a data frame, which unlike a matrix, actually considers the rows to be observations and the columns to be variables. So they're explicitly recognized as being observations versus variables. So we just want to maintain that format by using the as.data.frame command, which converts the matrix produced by scale to a data frame, and then we assign that to back to CS11. So CS11 is now a data frame with standardized variables. Okay, so now we're going to calculate Cronbach's alpha. So I mentioned it's not the best thing to rely on, but we're going to use it for part of our scale construction and assessing reliability. So let's calculate that. So we do that by running the alpha command. So we apply the alpha command to the data set, which is CS11, and then we assign the output to alpha underscore CS11. So now the output from alpha is there. So it contains the alpha coefficient and a few other things, some of which we'll use in a minute. So let's run that. And now we'll look at the coefficient. So to get the coefficient, you have to use the subset operator, which is the $, and then the name of the subset, which is coefficients. And if you just run that, it tells you that Cronbach's alpha is 0.76, which is actually pretty high. But we're not just going to rely on that. That's a very limited measure of reliability with scale. It's just very preliminary, but we'll look at that in a minute. Okay, so let's actually create a scale. So this is if we create a semi-rating scale by averaging across a number of items. So within a row. So to average across a number of items for various observations, we use apply. So apply basically applies a function to a number of rows. And so the function here is mean, and we're telling it which dimension to apply to, the margin, and rows are dimension 1. If you want to do it to the columns, it would be dimension 2, margin 2. And here's the data set we're using, CS11. So we apply that, it calculates the means for each row, and then it assigns the output to an object called scale. So let's run that. Now we can get some summary statistics of the scale. So let's see what summary does. So summary tells us minimum, mean, median, maximum, and then SD. If we run that, it gives us the standard deviation of our scale. The next command allows us to create a histogram of the scale. So the histogram command is part of the lattice package, and it gives us a nice histogram. So we can see the distribution on our scale, which we have right there. Are there any questions so far? Everyone's okay? Okay, now that we're going to do the item analysis of the scale. So remember, the item analysis is how we assess the reliability. Remember, ideally we want there to be a monotonic relationship between each item and the underlying dimension. So we do that by creating rest scores. So rest scores are the scale without the item, without each item. So we're going to do that first by looking at Cronbach's alpha. So we're going to calculate, actually it's already been calculated, it's actually part of our alpha underscore CS object, but now we're going to set that like con alpha, conditional alpha, which is alpha without each item. So now if we run that, we can see the alpha score with each item removed. So for item 1, if you take it out, this is the alpha. For item 2, this is what it is. And interestingly enough, we see, if we remember what alpha was, it was about 0.76, it goes down each time we remove an item. That actually is a good sign. If you see that alpha goes up when you remove an item, it means it probably doesn't belong there. Although it's not the only criterion, because we should also look at graphs, because we want a monotonic relationship, but this is a good sign. If we see that they all go down, that means that those items should probably be there. If it goes up, you'll want to make the graphs, and then you might want to consider removing them and then running the whole process again. So since we wanted a monotonic relationship and not just look at correlations, which measure linear relationships, we're going to look at some graphs. The commands to make the graph are a bit complicated. There was actually Dave Armstrong, who teaches the scaling course at ICPSR, wrote a good function to do this. And if you have the code file restplot.r, you can just load that in by using the source command, and then you'll have access to a function called restplot. Does everyone have that code file? And if you have it in the same folder, it'll run right away. So just run source, and then run this command. So it creates rest plots for this data set, so this set of values, and it applies some jitter to move the points around a bit, and it creates this table of graphs. So now you see the relationship between each variable and the scale minus that variable. So let's zoom in to get a better look. So we see that in all cases there is a monotonic relationship. So it goes up all the time. So it's always either positive or sometimes it flattens out a bit, but it never actually goes down. So that's exactly what we're looking for. That is a monotonic relationship. So we want to keep all these items. We found that alpha doesn't go up when we remove any of them, and we also find monotonic relationships. So if we found that alpha went up when we moved an item, and then we looked at our rest plots, we found that one of the items, and actually the same item, did not have a monotonic relationship. What we do is we remove that item, and we go through the process again. And we want to see if, once we do it again, whether any of the items increase the alpha when we remove them. And then we would want to look to see that there's a monotonic relationship. And if that is the case, then we keep that scale. If none of the items lead to an increase in alpha when we remove them, and all of them have a monotonic relationship, we keep those items in the scale. Then we might have to remove more if we don't find that. If we find that removing one of the items leads to an increase in alpha, and we find a non-monotonic relationship between that item and the underlying scale, we remove that and we run it over and over again until we find that alpha doesn't increase and we find monotonic relationships. That can be a problem if we run out of items. That probably means that there's a problem with those items, and you might not want to create a scale out of them. And you might want to use a different scaling technique. Okay, so that's it for summative rating scales. Does anyone have any questions about that?
So, yeah. I've just looking at the graph.
Yeah.
Do you take into account the fact that some items may have more variance around their estimated? The line was kind of a regression line or something. So
right.
Do you take into account the variance around it, or say an item may have less variance around its regression line, so it's more accurate as in it's a more accurate item for the scale, or do you take it into account in the technique? Or?
Well, it's a summated rating scale, and it's the simplest type of Likert scale. So basically, just adding them together. There are more sophisticated techniques that take into consideration, how good each item is, how hard the test items are, for example. But in a Likert scale, it's essentially just adding them together. Each item counts for the same amount, and we just take an average. But yeah, there are more sophisticated techniques we could do that, but we won't be seeing them today. Okay, any other questions? Let's move on to our next scaling technique. And once again, this is for the same kind of data, so single stimulus data. So here, so remember, once again, it's the same idea of measuring objects on one or more dimensions. And here, unlike some of the rating scales, what we do is we actually assess dimensionality with principal components analysis. And a lot of people confuse this method with factor analysis, and hopefully, in the next few minutes, all of you will understand how principal components analysis is not the same thing as factor analysis. So here, we're actually assessing dimensionality. So remember I said that there could be, when we're measuring each unit along dimensions, it could be one dimension, it could be more. Here we're actually allowing the possibility there's more than one. So here essentially what we're doing is we're looking for orthogonal, meaning uncorrelated, variance maximizing components. So we're looking for different components that capture the maximum variance. You'll understand this, we'll go through lots of examples, and it'll be clear that essentially we're looking for one component that captures a lot of variance, the second looking for another one that captures a lot of variance, and all of them are orthogonal, they're uncorrelated. And the idea is to account for all the variance in the end. But we want to do it with as few components as possible, but we will account for all the variance. That's what principal components does. Factor analysis doesn't do that, as we'll see in a minute. Each component is essentially a linear combination of the variables. So we can see each component as being basically a linear combination. So you add the variables together, the coefficient, you produce the components. And these coefficients are called the loadings. So we say each variable loads on whatever component by whatever amount. Principal components analysis, unlike factor analysis, is totally atheoretical. We don't have a theory behind it to say that there is one latent variable that explains things. So there are two latent variables. That's factor analysis. Here we're just trying to account for variance. We will end up with components which we can try to interpret, but really there's no idea that there actually is something in reality that is behind our variables. Here we're just trying to account for variance. So there isn't a small number of latent variables, we're just looking for components that soak up, that capture that variance. Okay, so essentially what we're doing is, I explained this a bit, we're looking for a first component that accounts for as much variance as possible. So it could be very little, or in some cases it could be 60–70% of the variance, sometimes it happens, it really depends. And then once we've found a first component, we'll look for a second one. But the condition on that second one is that it has to be orthogonal to the first, it has to be uncorrelated, totally uncorrelated. And we look for a second dimension that accounts for the remaining variance as much as possible. Then once we've found the first two components, we look for a third component, which is uncorrelated with the first two, and that accounts for the most variance left over. Then we look for a fourth component that's uncorrelated until we've accounted for all the variance in our variables. You have to account for all the variance. That's what factor analysis doesn't do. Principal components accounts for all the variance. So we end up with all these components which are orthogonal and which account for all the variance in our variables. Before we do principal components, it's really important that we standardize our data, our variables. Otherwise, the variables with the biggest variance will be most strongly related to the first component, and they'll basically dominate the first component, which we don't want. We're trying to find variance that is common to the variables. So basically, the major goal behind principal components analysis is to explore the dimensionality behind our data. We want to see how many important dimensions there are. And we find there's a small number of dimensions that can account for our variables, that can capture their variability. We might use that to reduce the dimensionality of our data, to provide a simpler representation of our data. But that doesn't always happen. We might find that it takes 5 components just to account for half the variance, in which case it's not very parsimonious and it doesn't really help us very much in terms of data reduction. So it doesn't always work that well in terms of reducing dimensionality. But I mean, ideally, we would like to do that. That's the major goal in scaling. So we would like to do that, but at least we're exploring the dimensionality. It's our minimal goal here. So it's only really data reduction if you have a small number of components that capture a lot of the variance in the variables. So essentially, normally what we're trying to do is trying to express k variables with less than k variables, and which are all orthogonal. That's essentially what we're doing. So if we have less than k variables, we're reducing the dimensionality. Hopefully it'll be a lot less. Hopefully it'll be 2 or 3, which makes things a lot easier. Okay, so now let's move on to, we'll move back to R. Yes, go ahead. Yes.
I just want to make sure, what relation can we expect between the alpha and the principal component analysis? Let's say we have an alpha of 83 or 84. Should we expect to have very few components to come out of it, or it can be random? There is no clear relation.
That is what, I mean, the problem with alpha we're talking about subject rating scales, I mentioned that often there'll be false positives. So alpha can be really high just because there happens to be clustering. So if you have 2 clusters, that can be 2 dimensions. So you can have an alpha of 0.7, 0.8, just because there are 2 clusters, and those 2 clusters can represent 2 different dimensions. So it doesn't necessarily mean that there's going to be one component that captures a lot of the variance.
Okay. And with the alpha, we know that the more items we have in it, the more likely it is to be high.
Yeah.
Is it the same with
the more items, the more components it will be?
No, the more items, the more the first component will explain.
Not necessarily, because it depends. I mean, it's very variable.
There's no clear relation between the two. First, say.
When is more explained by the first component if you have more items? I don't think so. I mean, if you have more items, you probably have more components. And then how much the first component explains really depends on the variable.
Right.
It's extremely variable.
Thanks.
Okay. Does anyone else have any questions? Alex, does that answer your question?
It's clear. Very
Okay.
good. Thanks.
Great. So let's look at some examples in R. Okay, so now we're going to use a different data set. We're going to use the data set from the 2012 convection election, the survey done by the Make Electoral Democracy Work project, and we're going to use some particular questions. We're going to use questions asking respondents to tell us how much they like or dislike each of the parties and each of the leaders on a scale from 0 to 10. So if someone says 0, it means that they really dislike the party or the leader. If they say 10, it means that they really like them. So I've taken these out, I've made them numeric, and I've taken out the missing values, the same thing as I did before. So we have that data set is called QC12. So once again, if you have it in your working directory, and you set your working directory to the, if you have them in the same directory as your code, and you set the working directory to that folder, you should be able to just run this. So read.dta on the file, and then you assign that to QC12. So now QC12 is the object containing our data set. For now, we're just going to work with like-dislike ratings of the parties. So as I said, we also have them for leaders. We'll look at those later. But for our principal components analysis, we're going to keep things really simple. And we're just going to look at the parties. So to select ratings only of parties, what we do is we're going to subset the data set. And the way you subset in R is by using square brackets. And square brackets allow us to put in the indices for the rows and the columns we want. If we want to take rows, we put the index before the comma. If we want to take the columns, we put them after the comma. And so the indices here are 2 to 7. We want columns 2 to 7 of QC12, and then we assign those to object LD. So LD contains those columns. So the 6 columns, right? Yeah, with just the variables on party evaluations to help people feel about parties. And now we're going to run principal components on that data. So here the command is printcomp, and we run it on the dataset LD. As I said before, principal components should be based on standardized variables. There are actually 2 ways you can do principal components. You can use correlations or you can use covariances. If you use covariances, it's really important that you standardize the data. If you use correlations, it actually does the same thing. So you can just put core equals T, and it uses correlations and basically standardize the items. So you don't have to worry about one one variable taking over one of the components. So we write principal components, and we assign it to ld.pca, to that object. And now we want to get a summary of the results, which are stored in that object. And here we see first a summary of the components. So we see the standard deviation of each. We see the proportion of variance each of them explains. So the first component explains 53% of the variance in the variables. The second, 15.6. And we also have a cumulative proportion. So we see that with the two components, we can explain 68.7% of the variance in those items. Below that, we have, since we used the loadings equals t option, we have the loadings. So we have the loadings of each variable on each component. So here we know, we know essentially the coefficient, if we were, before we saw the equation, how each coefficient relates to the variables. Here, these are those coefficients. So this tells us that variable 1 loads 0.4 on component 1, variable 2, values of the BQ is minus 0.446, and so on. So that's really interesting. We can try to interpret our components. So the first one appears to be something like a left-to-right dimension. So we see it's evaluations of the Quebec Liberal Party, really high on there. Evaluations of the CAC. I mean, it's positive, it's weaker, but it's still positive. And then all the other parties, which are more to the left, load negatively on that component. So it seems to be left-right. Now for the second component, it seems to be associated more specifically with one particular party, the CAC, which is very negative on that component. The PQ is very, very low but weak, very low but very weak but negative, and the Quebec Liberal Party, relatively weak, positive. So I don't really tell you so much, but it really seems to be associated with that particular party, with the CAC. Now we'll see what we can do with those components. We can visualize them graphically by creating a biplot. Has anyone ever seen a biplot before? It looks really messy there. I'll zoom in and I'll show you in a minute how to clean it up to make it a bit more interpretable.
Biplot?
A biplot. BI plot. So a biplot shows you can actually do this in 2 dimensions or in 3 dimensions. It shows you how each respondent relates to the components. So the score of each respondent on each component. So those are these numbers here. So the numbers represent respondents. You can change it to put dots, whatever you want. So if you look here, 332, its score on this component is just below minus 0.05, and its score on component 2 is about minus 0.01. And it also tells you how much each component explains the variance in each variable. So each variable is represented by a vector. So evaluations of the CAC are represented by this vector. So this shows you the variance in that variable. And we see that there's a relatively small part of the variance in voting for the evaluation of the CAC, which is explained by the first component. So it would be how much, how much is explained along this axis here. So it's the difference between the tail and the endpoint. We see that. And we see that more of it is explained by component 2, which we see on the other axis. The Quebec Liberal Party is the opposite. PLQ, we see most of the variance is explained by the first component, while the smaller amount is explained by the second component. Is that clear?
Je donne ça à saisir les lignes. Ok, donc, là, il y a QS, ON.
Ouais, ici c'est un peu serré, donc on voit pas très bien. It's a bit, everything is really close. What I'm going to do now is I'm going to hide the points because we don't necessarily want to see the points of representing respondents, and that way it'll be a lot clearer because now we're only going to have the vectors for the variables. And the way we did that is I changed the colors. So I made by saying I created a vector of colors. So white is for points, black is for vectors representing the variables. So now what we have is a graph with points that are white, so we don't see them, and we just have our variable vectors in black, so we do see them. I think this is clear, right? So now you can really see much clearer how much of the variance in each variable is accounted for by each of the components.
So this is why GP always talked about doing it three-dimensional, you know, because if you wanted, you could have a third dimension and then have your box like GP's doing, right?
Yeah,
Yeah.
you could do 3 dimensions. In general, we try to avoid 3-dimensional graphs. One thing, in my last workshop we talked about lattice, and lattice is generally, there are 3-dimensional graphs you can make, but lattice is generally made not to. It's actually made so you divide them and you create 2-dimensional representations, and like to represent 3 dimensions, maybe more dimensions. It's generally better. But in terms of making 3 dimensions, you have 3 dimensions from principal components. Remember how much variance is explained by each component. We see that here. So the first component is 0.53, the second 0.156, and then 0.136. So it really gets smaller and smaller. So you really have to decide, does it make sense to include an extra dimension? You see that it goes down. In this case, there isn't a big difference between the second and the third in terms of variance explained, but the marginal value of adding an extra component isn't necessarily that high. So you might want to, you might just want to forget about those. If you want to see the respondent's scores on each component, you use you take the output from the principal components analysis and you subset it using the name scores, and you get this here. So you get a score for each individual on each component. What's really cool about that is you can actually append those to your data set. You can add the scores to your data set and you can do all kinds of things with them, like running models. So here what we're going to do is we're going to take those scores. So we say scores, we'll take the first 2. So scores subsetted 1 and 2. And we assign those to our data set, and we say we assign them to columns called comp1 and comp2. Okay? So now those scores are in the data set. Now what we're going to do is we're going to run a model. So what we're going to do is we're going to regress vote intentions for the 4 main parties on those 2 components. And for those of you who took my last workshop on R and graphs, you already know the effects package that allows you to get really easy graphs to represent the effects of various variables. So the command to run a multinomial logistic regression, which is what we're going to use, is in the nnet package, so we just load that. And now we'll run the model. So the command is multinom, and we run it on this object here, which is the dataset QC12. And we tell the command to interpret the data set in a particular way, which is vote is an independent variable, which we're regressing on these 2 variables, component 1 and component 2. And then we assign the output from that regression to object mod1. Now, we're just going to look at the effects. First, we have to load the effects package. And then so the command all effects, I didn't talk about this in my workshop on that, but all effects, essentially what it does is it calculates the effects of all the variables. And then when we use the plot command, we can actually plot that. So here's very small, I'll zoom it in. So here we see the relationship between each of our components and the different categories of the dependent variable, which is vote intentions, for the 4 major parties. So we see that as scores go up on the first component, the probability of voting for the CAC increases. The probability of voting for the PQ decreases. The probability of voting for the Quebec Liberal Party decreases as well. And, QS, Quebec Central decreases, PQ decreases, the names at the top, Quebec Liberal Party increases. So it's really consistent with the notion that it is a left-right scale. If we look at the second component, as scores increase, the probability of voting for the CAC decreases, the probability of voting for Quebec Solidaire increases. There's sort of a curvilinear relationship with probability of voting for the PQ. It increases, then decreases. Probability of voting for the Quebec Liberal Party increases. So it sort of seems to be really associated with voting for the CAC, that the higher you are on that component, the less likely you are to vote for the CAC. But we'll be looking at the same items for a number of different, for the two other models we'll look at, which are factor analysis and multidimensional scaling, and it might help us get a better understanding of what they actually represent. Now we're going to take a very quick break, 5 minutes. So at 11:13, come back and we'll continue with factor analysis and then multidimensional scaling. Unless there are any questions? No? Okay, 5 minute break. Okay, so now we're back. Let's look at our next technique. Now we're going to look at factor analysis. Who's heard of factor analysis? Great. What we're going to look at today is also called exploratory factor analysis. We're not going to look at confirmatory factor analysis. So hopefully you already understand that factor analysis and principal components analysis are very different. Over the next couple of minutes, you'll see some of the major differences. If they haven't been clear enough, they'll be clear very soon. So with factor analysis, the goal is to find factors, which we can see as latent causes, that are common to two or more indicators. Okay? So we have a number of indicators, a number of variables, we want to find out what causes them. They're actually, unlike principal components analysis for a number of variables, there are actually many different solutions. So we call that factor determinacy. There isn't just one way you could do it. You can actually rotate the axes, you can do a lot of things, which we'll see in a minute. So principal components analysis, rather than looking for underlying latent variables, we were trying to account for variation. We were trying to find components that account for as much variation as possible. In factor analysis, we're actually looking for underlying causes. We're not trying to capture all the variation. And actually, as we'll see, there is this idea in factor analysis that there is unique, specific variance to each variable that we're not trying to capture, that we're not trying to find a common factor that explains those. We actually accept that there is unique variance for specific variables. So the basic assumption in factor analysis is that all variables are caused by the same static source. So 1, 2, maybe 3 factors, and that those factors actually exist in the real world. In principal components analysis, we're just looking at those particular variables. We're asking what are the sources of variation in those variables. With factor analysis, we're actually assuming that there are factors, there are latent causes of those variables in the real world, that these things actually exist. That is not just something in our sample, it's not just something in with the particular variables we have. Principal components really depend on the variables. You change the variables, you change the components. They don't necessarily represent anything real in the world. Usually, we want to find fewer common factors than we have observed variables. That's the goal behind this, is to find causes of multiple variables. Okay, so as I said, in factor analysis, we're not trying to soak up all the variance. We accept that there is specific variance for particular variables. So we can split the variance, the total variance, into 3 components. So there's the common part, the part that is explained by one or more factors, which is also called communality. There's a specific variance, which is specific to a particular variable. And there's also random measurement error. So there are those 3 components. So communality is the amount of variable variance that is derived from a common source, that is actually shared with other variables, as opposed to specific variance. In principal components analysis, everything is common, because we're trying to find components that account for all the variance and all the variables. Unique variance is specific to a particular variable. When we do factor analysis, we end up with two matrices, which are interesting. There's a factor pattern matrix, which gives us the loadings. It shows us the coefficients, giving us the loading, how each factor depends on, or each variable depends on the factors. And then there's a factor structure matrix, which is a matrix of correlations between factors and observed variables. So we can think of factor pattern matrix as being coefficients, like in a regression, and then factor structure matrix as being a matrix of correlations. It's basically the same thing. Just one are coefficients, and the other one are correlations. So under principal components analysis and factor analysis, we can actually rotate the axes to make them more interpretable. And essentially what we're looking for is simple structure. Simple structure basically means parsimony. It means that we're trying to have factors that affect as few variables as possible, and we're trying to explain each variable by as few variables as possible, as few factors as possible. That's our goal, to associate as few factors with as few variables as possible. Essentially, what we're going to see is, when we graph this, we end up with clouds, we call clouds of vectors. So vectors in a 2 or maybe more dimensional space, and we want those vectors to go through our axes. That's our goal. So we rotate the axes so that they correspond as well as possible with the vectors representing variables. There are two major types of rotation. There's varimaps, which is orthogonal, but there are also oblique rotations. We don't necessarily have to have orthogonal components. We can rotate not those factors. We can rotate our factors, our dimensions, our axes, so that they correspond with as well as possible with the variable vectors in a way that it doesn't respect orthogonality, which is actually different, another difference between factor analysis and principal components. Here, the dimensions do not have to be orthogonal, whereas in principal components they are. We end up with factor scores, which are the estimated values of the linked variable for each observation. They're similar to component scores. We had principal components, so we can actually place each individual along the factors. Are there any questions?
Yeah.
Yeah.
Can you clarify what is oblique rotation?
Oblique rotation is essentially rotation that tries to make the axes go through the variable vectors without it being orthogonal. So if it's orthogonal, the factors, the axes are always going to be orthogonal, uncorrelated. But if it's oblique, they don't have to be uncorrelated. They can be correlated. So we'll see this in the example. It will rotate the axes to fit the variables as well as possible to create a simple structure. So have as few variables explained by each factor and as few factors explaining each variable as possible, and it'll do that not necessarily with respecting orthogonality. We'll see what it looks like in the examples.
And is there just about this issue? I remember the literature. Is there a recommendation? Should we or shouldn't we rotate? Do we know exactly?
We should, because we want to create a simple structure. That's what we do in factor analysis. We generally should rotate.
But like you might want to rotate it so that they're orthogonal, or you might.
Yes, that's what the sort of another issue. If they're close to being orthogonal, you might want to respect orthogonality, even though it doesn't provide the simplest structure. But it's generally better if they're not close to being orthogonal. It's better to rotate because you want to create something more interpretable and you want a simple structure. But there's sort of different views on that. Not everyone would agree with that. But generally, in factor analysis, the idea of orthogonality is really important. That's a principal components issue. Okay, so let's do some R stuff now. We're going to go back to the same data, except now we're going to take like-dislike scores not only for the parties, but also for the political leaders, the party leaders, from the same data set from the 2012 Quebec election. So now we're going to subset the data, taking columns 2 to 12, which correspond to the party evaluations and also the leader evaluations, and we'll assign those to object LD2. So we're going to start our factor analysis by creating a matrix of correlations among all the variables in that data set. So we do that using the core command. So we apply to the data set, we assign that to object R. Now we're going to calculate the specific variance for each item. We do that using this code here. I'm not going to go through it because it's a bit complicated. Just all you have to understand is that this tells you the specific variance for each variable. Then we assign that to psi2 hat. Then we're looking for communality, the amount of variance that is shared in common by the variables. And we do that by subtracting the total correlation matrix from the specific correlations, which gives us a reduced correlation matrix. So it gives us this correlation that is shared by the different variables that is specific to them. Okay, now what we're going to try to figure out how many factors best represent our variables. And to do that, what we do is create a graph, a plot called a Screenplot. Has anyone heard of a Screenplot? So a Screenplot basically tells us how much you get in terms of explaining variance from each additional factor. And we do that by calculating eigenvalues. There's a whole math behind this, which we're not going to go into today, just so you know that it's based on eigenvalues. So basically plotting eigenvalues. And then we create this here. So this is a Screenplot. So this tells you how much you get out of each extra factor. And basically we stop when we get the first bend. So we look for bends in the plot and we find one here, so we'll stop there. Often you'll actually take the preceding one. You won't even go, you won't even take the one at the bend, you'll take the one before. But here it's at 2, which is a small number, it's quite parsimonious. So we'll take 2 factors. We could actually probably represent this pretty well with 1. But 2 is parsimonious enough for us. Any questions about that?
I think there's also people say that anything that is above 1. All right.
That what's it?
Anything above 1 and anything that has a negative value above 1 can be considered
Yes.
another way to discern.
There are actually, there are a number of different rules for deciding how many factors. It can actually also come from theory. So there's empirical rules based on things like eigenvalues, looking at them in terms of the value or the Screenplots, or it could be based on theory. You could have a theory that there are 2 factors and 3 factors, and you want to use those. So there are a number of different ways. So we're actually going to calculate the factor analysis. The command of factor analysis is FA, and that's in the site package, so we're going to load that. And now let's calculate the factor analysis. So we use the FA command on scale, so standardized variables here in this data set. We set 2 factors, and we set rotation to 9. Later we'll try some rotations and see what it gives us. So now the results are in FA1. And now we look at the loadings. So to get the loadings, so how each variable depends on the factors, so the coefficients. On those, we use the loadings command, we apply that to the output of our factor analysis. And now we assign that to an object called lambda, because lambda is generally used for the coefficients. And now we just type lambda and we see those loadings. So we see the loadings of each variable on each of those factors. So we see the first factor, it seems to be associated with parties generally on the left and leaders more on the left, but it's negatively associated with basically variables representing parties on the right and leaders on the right load negatively on the factor. Now if we look at the second component, we see that it is again associated with the CAC and its leader. In a much leader way with PQ and with François David, leader of Quebec Systems Analysis. It's similar to the physical components, it seems to be associated with CAC.
So all the parties which there are no values, is that because they're not associated with the second component at all?
Well, second factor, yeah.
Yeah.
So the factors don't have to explain all the variables, they can explain only some of them.
Okay.
Yeah, that's right. Now let's get a plot. Let's plot the results. So this is a bit complicated. So first we create a blank plot, then we add the arrows, and then we add the axes, and then we add text representing the different vectors, different variables. I won't go into that in detail. So here's our plot. So here it's sort of hard to see each variable because they're very close together. But here we see that this isn't a very simple structure. One thing is, this here doesn't really correspond to the axis, and this here is a bit off the axis. This is pretty close. So we probably want to rotate this, because this is sort of hard to interpret. So what we're going to do is we're going to rotate our axes and see if we can create something easier to interpret.
It's like fairly similar to what we got from the principal components.
Yeah.
It's just the parties.
Yeah, actually, yeah, so now we have a few other variables, so it's just the leaders don't really change much, but also the math behind and the calculation behind factor analysis, principal components analysis are actually quite similar. It's just that we're just doing something different. Mm-hmm. So if we're looking at 2 components versus 2 factors, we'll find something very similar. Mm-hmm. Okay, so now let's try a Promax rotation. So Promax, remember, was an oblique rotation. So it doesn't have to be orthogonal. So let's just do that directly. So we do factor analysis, we assign it to an object called 2, and now we put rotate equals promax. We do the exact same thing as before, and we just make the graph directly. And now we find that the variable vectors are much closer to the axis, so it's much easier to interpret. So this here, something seems to be left, right, although it's sort of inverted. Left is right and right is left. But that's pretty easy to interpret. Everyone's on the left is there, and everyone on the right is here. And then the second factor is clearly CAC. And it's quite easy to interpret.
How would you interpret that?
I'm sorry?
How would you interpret the second factor? Substantially.
Well, I would say there's something underlying support for the CAC that is distinct from other parties. Actually, when we do the MPS, we'll see that there's sort of a second dimension that is underlying support for the CAC, but in a weaker way support for the PQ. This was in 2012. There's something else. We can try to interpret it substantively. I actually have my own interpretation, and it might explain the strategies adopted by the parties, the governing party in particular, to try to get certain votes, because we see that it has something in common with the CAC. It's less associated with, it was less associated with 2012 with the PQ than with the CAC. And here in the factor analysis, we don't really see this associated with the PQ at all. But when we get to the multidimensional scaling solution, we'll see that it does seem to be something that the PQ and the CAC have in common. Now let's look at a varimax rotation. So a varimax is orthogonal. So it's a bit stricter than the promax oblique rotation. Let's just run through it and graph it. So here it's pretty good. Maybe not quite as good as the promax rotation, but it's pretty close. It's still pretty easy to interpret. So here it's really up to you. If you want to respect orthogonality, you can take this one, these results. But if you want something that's the simplest structure, you could just take the second one, the one with promax. I decided to take actually I wanted to take varimax, but I actually took the took the promax results.
So it's the same as the.
Oh, sorry. What did I do? No, actually, I didn't show you the right result. Okay, so this is the varimax. So this is the orthogonal. So it's not perfect, but it's still sort of acceptable. You might want to take that. What I meant was, okay, let's decide we're going to take the promax because it looks like the best, simplest structure. What I made a mistake was here. Here, if you want to see the scores, there should be a 3 because FA3 was the actually it's like promax. Actually, no, it wasn't this one. This one is fine. It's here. This should be FA2. Okay, so we want to get the scores from the promax rotation. We take the output of the factor analysis, which is FA2, and we set it as say scores. So these tell us the scores of each respondent on each of those two factors. We can add these to our data set, which was the same thing we did with the principal components. So we can add them to our data set, so we can run models with them by assigning them to variables in the data set. So here we say, take score 1 from here and assign it to variable f1, take score 2 and assign it to f2. And now we can actually run models with those. And now we can run regression models. We'll do the same thing as before. Run a multinomial logistic regression with the two factors as our independent variables. So run that, create effects plots, and see how those look. So now looking at our first factor, we see that that it clearly increases. So the probability of voting for the PQ clearly increases when someone scores higher on that on factor 1. Probability of voting for the PLQ, the Liberal Party, decreases. Probability of voting for Quebec Solidaire increases. CAC, it's sort of curvilinear. it's not too clear. So this seems to be maybe a bit less clearly left-right than before, than with the principal components, but it still seems to be generally left-right. Does anyone disagree with that interpretation?
Well, I mean, it could be both left-right and sovereignty federalism sort of together.
It could.
That would explain why the cap is
is
sort of curvilinear,
right.
because
But though if it was left-right, then I would expect US to be
Yeah, that's actually a good point. Yeah.
stronger. Yeah.
Yeah.
so maybe this is actually like something like sovereignty federalism.
Yeah. It could be. And then so the second, it often is hard to interpret them.
Right.
Now, looking at the effect plot for the second factor, we see that's clearly associated with voting for the cap. So the higher you score on there, the more likely you are to vote for the cap. Makes you slightly less likely to vote for Quebec CÉCD, less likely to vote for the PQ, and less likely to vote for the Quebec Federal Party. So again, it's sort of like a CAC factor. It's sort of like a unique thing that party has.
You say that now this effect is a switch to the PQ, or on more recent data, or?
Oh no, what I was saying is that in the last technique we used, multidimensional scaling, we'll see that there is that the PQ and the CAC do share similar positions on the second dimension.
Could it be that the second dimension is some sort of cynicism toward the existing party system, so that people who don't like liberals and don't like PQ because these are old parties that just go to the CAC?
Although, I mean, shouldn't it also be associated with voting for QS, for Quebec CÉCD?
Yeah. Should it?
It's also, again, the party, relatively new, which...
I would call
There's
that
something
popular.
less cynic in QS. Am I right? I feel like there's something less cynic about Quebec CÉCD.
About the kinds of voters? Yeah, I mean, so it's not necessarily about insider parties, it's people related to a specific kind of party.
It's not even loading on QS.
Yeah, there's no relationship.
It's flat,
Yeah, but I mean, what I'm saying is that if it was really, numerous old parties would expect the probability of voting for Quebec CÉCD down to go up as people's scores go up as well. So it's not really.
Maybe a last question.
Yeah.
To have a better understanding of what is the, let's say, latent meaning of each these factors, would it be better to add control variables, like 10 control variables, so that we could make sure that these are not, say, the people from the area, or you're just doing bivariate.
We're not going to say, but often when you want to do doing a factor analysis is make sure that the differences, the factors are due to different groups. I wasn't planning on talking about that,
Okay.
but it is, yeah, it actually is an important point. You should check for that. Just we're not going to talk about that today.
Okay.
You want to make sure that the dimension is represented. Yeah, it is representing different groups. Okay, let's move on. We have just over 20 minutes. Let's move on to our last scaling technique, multidimensional scaling. Has anyone here ever done multidimensional scaling? Okay, this is really cool. It's good that no one's heard of it because I'm going to teach you all something totally new. So essentially, multidimensional scaling is, there are a number of different techniques it could be. It's sort of a family of data analysis methods, this is the way Young defines it, which all have in common the fact that they want to show a data structure in a spatial way, which is easy to understand by anyone. So the idea is it's all about making a visual, creating a geometric representation, because it's very easy to see things. You see a picture and it's just so clear. Whereas when you have a matrix of numbers, it's not that easy to understand. But if you create a picture, it makes it very easy to interpret. So the type of data we use here, remember I talked about single stimulus versus similarity data, with those two types of data we're using. So up to now we've been talking about single stimulus. Now we're talking about dissimilarities data, which could also be called proximity data or similarities data. Basically, the idea here is that we're looking at different units from the same set, and we want to see how similar or how different they are. So, I mean, the units can be very different things. I've seen multi-dimensional scaling applications where they looked at distances between cities. So they're taking the distances between cities and they created essentially a map of the US or of the world. It's really cool because it's actually geographically accurate. You take the distances between cities and you can reproduce the United States, a map of the United States. So they could be that. It could be differences in the perceptions of parties, which is what we're going to look at. We're going to look at parties and leaders. We look at how similar are the perceptions of parties, or how similar are the likes, dislikes of parties and leaders. But basically, the data we use are matrices of dissimilarities. So the data, so in our matrix, the numbers should get closer when the objects are more similar, and they should get the numbers should get smaller when the objects are more similar, and larger when the objects are more dissimilar. So if cities are further apart, the numbers should get higher. If they're closer, they should get smaller. Essentially, there are two purposes, and here I'm citing Borg, Gronin, and Mayer, who said the purposes are, first, we want to visualize proximity or dissimilarity data to make it easier to interpret. Another thing is we want to uncover the dimensions of judgment. So we want to uncover the dimensions behind people's evaluations of parties, for example. So we assume that there are psychological dimensions behind people's judgment. So why people say that they like party A but not party B, or why they say they like party A more than party B. We assume that there's dimensions behind that, and we want to find those. And we get that by creating this visual representation of our data. So you can really think about just the map. So what I was saying about using distances between cities is really cool because you think, normally when you have distances, it was calculated from a map. So you take a map and you look how big the distance is between them, and then you apply a scale, and then you figure out the actual distance. Here we're actually doing the opposite. We're taking the distances, whether between cities, between political parties, whatever, and then we produce a map. We produce a visual representation of those distances. Okay, so basically what we're doing is we want to place the objects in a geometric space in such a way that the rank order of the distances between the objects corresponds to the rank order of dissimilarities. So we know, we can rank the dissimilarities. So we know which two objects are the most similar, the next most similar, the third most similar, the fourth most similar. We have a rank order of them. Now, what multidimensional scaling does is it creates a geometric representation that respects that rank order. So the distances will be in the same order as the dissimilarities. So if we were to rank the objects based on the distances, it would be the same rank order as for the dissimilarities. And it makes it much easier to interpret, as I said. So you start out with you could have correlations or whatever, and then you display that rapidly, and it just makes it really easy to interpret. The input data can be ordinal or can be interval/ratio, but the output distances are always interval ratio data, which is really neat. So you can actually use ordinal data. If you're not sure, you can try both types of multidimensional scaling. So there's metric and there's non-metric. You can try both, compare them, and try to see which assumptions are being met. So metric multidimensional scaling takes interval or ratio data. So here distances are basically a linear function of dissimilarities. So you would have a function mapping distances to dissimilarities, and it's a linear function. Non-metric takes ordinal dissimilarities. And the function here is monotonic. It's not necessarily linear. It's really important when you're doing MDS to have a large number of points, so you want to have as many as possible. If you have a small number of points, like if you have only 4 or 5, the problem is that you won't have enough constraint, so you could actually move the points around and still respect the condition that the distances are in the same rank order as the dissimilarities. So you want to have as many points as possible to maximize constraint. So there's only one solution that really makes sense.
Would it mean that you could map it in many different ways?
Well, you want to avoid that. So if you have 2 or 3 points, yes, you could do it in different ways. If you have enough points, there aren't too many ways to do it.
So what do you mean by constraint?
Yeah, so you want as many as possible to put as much constraint on the output. Any other questions? Okay, so this is my last slide. We'll move to R. Okay, so we started out with the same data we had before. So remember, it was a set of ratings, so like ratings of each of the parties. And now we want to convert that into distances, or actually first dissimilarities between the parties. We want to show how dissimilar the parties are. There's actually a function in R that does that. It's dist, D-I-S-T, and what it does is it calculates the distances among the rows of a data matrix. The way we do it is first we have to take the transpose of our matrix, because it calculates the dissimilarities among the rows and not among columns. Originally, in our LD2 matrix, actually it's a data frame, we have the variables and the columns, but we actually want to find the dissimilarities among those variables, which are the columns. Dist works on the rows, so we have to take the transpose. So to take the transpose, we use the T function, we apply to LD2, and we create a new object called TLD2, which is a transpose of the original matrix. And now we use the dist command to parse that transpose matrix, and we assign the output to distmap. So now we have a matrix of distances. Let's look at it. Let's see what it looks like. So it's sort of hard to see because it's on a very small window here, but essentially these are the distances among all the parties and the leaders. These are actually the Euclidean distances. You want to know how it does it. And so these are proper input for multi-dimensional scale. Does everyone understand that? Okay, great. Okay, we're not sure whether the data are best interpreted as being metric or non-metric, as being interval/ratio or null. So what we're going to do is we're going to try both types of multi-dimensional scaling. We'll start with metric and we'll see how well it works, then we'll try non-metric and we'll compare. Okay, so first we have to figure out how many dimensions best represent the data. And similar to factor analysis here, we're going to use a Screenplot again. It's the same rule. So we calculate the eigenvalues and we plot them. Okay, so here we see an algebra at 2. So it suggests that 2 dimensions is the best. So anything beyond 2 dimensions won't really add anything, which is similar to what we found before. Okay, now we're going to run MDS, and the command we use is Smykov, which actually is, I think I wrote it out here. It means stress minimization using a complicated function. That's if you want to play Smykov. Okay, so we're going to load the library, the Smykov library. And the specific function we use is Smykov sim, which is for symmetric matrices. We run that on our distance matrix. We say 2 dimensions, we want to use metric, so equals true. This is the way ties are broken, and Verbo says give us a lot of output, and then we assign the output to metric. Okay, so metric, if we just click that, we see what happened. And what's really important here is the stress. The stress is measured goodness of fit. It's sort of like the R squared in regression. So this is really low, and we want low. Lower the better. And generally, there's a rule which is if it's below 0.05, it's pretty good. Here it's 0.027, so it looks pretty good. Now what we're going to do is we're going to get the point configuration. So our output was assigned to metric. Metric contains a lot of different stuff. And one of them is conf. So if we subset metric $sign conf, conf is the point configuration. It tells us the coordinates of the different points. So we want to make that a data frame, and we assign that to metric.config. Now to see those coordinates, we type in metric.config, and we see the coordinates of each party and leader on each of those dimensions. And actually, I don't do this, but it's the same thing as with principal components or factor analysis. We can actually take these and append them to a data set, and we can do regressions or whatever we want. Okay, let's graph the solutions. We're going to graph those the configuration along the 2 dimensions. And let's look at the graph. So this is the metric multidimensional scaling. We're not sure it's the proper procedure yet. But we see, so first axis really seems to be left to right. Am I not mistaken? Am I right here? And I'm just looking, where the Green Party is. It really seems to be left to right and not sovereignty federalism. That's my opinion here. And then the second axis seems to be something else. We see that the CAC is actually the similar level to the PQ. It's a bit further up, but yeah, it's similar. And CAC and also like, the reader, but not R on the PQ. I would suggest that this is something else, maybe like identity. So the further down you are, the more open you are maybe to diversity, or the further up you are, the more you're in favor of favoring one particular identity at the expense of others. Could be that, could be something else. That's just my interpretation.
I guess would be if you live in Montreal or not.
That could be. So some might be better to look within groups. That's a possibility as well. But then there is the PQ and François David is that low on there. So I mean, if it were whether in Montreal or not, you'd expect François David to be much lower down. So I mean, there's different interpretations. We'll talk about interpretation strategies in a minute. So that's the output of metric MDS. Okay, actually let's talk about the interpretation right away. Let's put it back and we'll talk about the interpretation. So you can actually interpret this in two ways. You can look at the axes, and actually you don't necessarily have to respect the coordinate axes. You can actually have axes that go like this, or whatever. It doesn't really matter. You can think about it any way. You can also think about point clusters. So here you sort of see there's sort of a QS. Here we don't see too many clusters, but this is like QS with the Mercadier and putting up Y with PQ, François Legault and the CAC, François Rennes and the PLQ. In other cases, there'll be more interesting clusters. So one way you can interpret them is in terms of clusters. But I think dimensions are sort of more common interpretation. And dimensions are really neat because one thing you can do is you can take it into external information. You could take external information, for example, coded electoral programs, so electoral manifestos, and you can have a code for each party on each dimension, a score for each party on each dimension, and then regress that on the dimensions and actually take those coefficients to identify the dimensions. So that's one thing you can do. We're not going to do that today, but that's one way you can interpret them. So you take external information like from party manifestos and you regress that on here and create some dimensions which are easier to interpret. Okay, so for metric MDS to be appropriate, there should be a linear relationship between the distances and the dissimilarities. So the way we verify that is by creating a Chevron plot. And we do that here. So first we calculate these values here. It's not too important to know what they are. And then we plot those here. So this shows us the relationship between the distances and the dissimilarities. It's pretty close to being linear. It's not quite linear. You could maybe dispute this and say we should use non-metric. I would accept this, and I would accept the metric results. We'll look at non-metric, and you'll tell me what you prefer. The non-metric results, we'll see. We'll see in a minute. Let's try non-metric. So we calculate the MDS solution, and now we plot it. Okay. Okay. You see, the plot looks sort of weird. If you really think that non-metric is appropriate, you might want to stay with this. But if you consider the Shepherd diagram from the metric to be acceptable, you might want to go for the other one because I think it's much more informative than this, which just looks weird.
Well, this also sort of looks like the factor analysis and the principal components, like with sort of like a 3 clusters,
right.
Like it's a similar, if you were drawing out like the directions, it would look sort of similar.
Yeah. Yeah, that's true. Yeah.
I don't know why that is, but it's interesting.
Yeah. Well, just so you could think about that some more and try to think why. Because they are very different methods, but the results, there's definitely a connection between what you find with factor analysis and what you find with MDS. So we plot that out. Let's make a shepherd diagram, and we'll see what it looks like here. Okay, there. So here's a shepherd diagram, and we see that it sort of does respect monotonicity, but it's not that clearly so. So I would argue that the shepherd diagram for the metric solution respects the assumption behind the model better than this one does. So I would prefer the metric one, because here, like, it really should go up, whereas here we don't really see that too much. It doesn't go down, but it really the point should really go up as dissimilarity with dissimilarity. So we should see a clear positive relationship between dissimilarities and distances. So that's it. Are there any questions about MDS or any of the scaling solutions in particular? None? Everyone understands everything? So hopefully you're ready to use some of these scaling techniques in your own work. If you have any questions, feel free to contact me. Hopefully you now know how to distinguish the different methods. You know that factor analysis is the same as principal components, that you know what MDS is, you know how to create summated rating scales, and you also know how to evaluate them correctly. So no questions? Okay, so that's it. Let's go for lunch.